Okay, folks, I was displeased over how I gave the solution to this problem in class. So what I'd like to do is, before we start tackling it, I'd like to derive a different version of the logistics growth equation. So I want to pick up with where we left off after we built the linear function that went with the growth rate. So we said that the rate of change was proportional to the population times this linear function r minus r over k times p. So when I derived this in class, or when we worked with it in class, we made some substitutions. For example, we said let a equal r and let b equal r over k, and we made some substitutions to find its solution, which is fine. But I'd actually like to not do the substitutions here and solve this slightly differently. When we do, and after I rearrange it, we will have a more useful equation of the logistics model in terms of the carrying capacity. Now, this only really applies to when you have a problem where you're given an initial carrying capacity, and that's not always the case. So, for example, if you look back at the example we did in class with the rate of infection, you don't really have a carrying capacity issue there. You have a proportionality between the number infected and the number yet to be infected. So there are different ways to express this logistics growth model depending on your specific scenario. But because our problem on the WebAssign involves the carrying capacity, I'd like to make sure that k shows up in my solution to this. So my first move, I think, is to go ahead and factor out this r. So that would leave us with r times p times 1 minus 1 over k p. So then if we go ahead and separate this equation, we get dp over p times 1 minus 1 over kp is equal to just r dt. And it's helpful if we leave this r here. It'll make the integration slightly easier. So the next thing we want to do is we want to go ahead and separate this by variables, or separate these fractions, decompose them. So if I have a over p plus b over, I think I want to do one other thing here first. Sorry. Before I do that partial fraction decomposition, let's go ahead and multiply both the numerator and the denominator of this by k. So this would give me k dp over p times k minus p is equal to r dt. So I distributed the k to both the numerator and the denominator, and to the denominator I chose to multiply it to the second factor and distribute it. So that's what we ended up with here. So now back to the partial fraction decomposition, we would have a over p, that's a over this first factor here, plus b over k minus p, that's the second factor here, and this needs to equal k over p times k minus p. So if I try that multiplying by the common denominator trick, we get a times k minus p plus b times p needs to equal 0p plus k. It's a 0 there. So this gives us that ak minus ap plus bp needs to equal 0p plus k. So from that we get the two equations that ak must equal k. So we get that a must equal 1. And from these two facts we get that minus a plus b must equal 0. Well, we just said that a has to be 1, so minus 1 plus b must equal 0, so that we get that b must equal 1 as well. So now we can go ahead and take our integral, or what will be the integrand, and break it up as 1 over p plus 1 over k minus p is dp is equal to r dt. Integrating both sides gives us the natural log of the absolute value of p minus the natural log of the absolute value of k minus p, where this minus sign here comes from the sort of u substitution that we do with this we've got the minus sign there, is equal to RT plus C. So cleaning things up, we can go ahead and combine these two logarithms as P over K minus P for the argument. Absolute value, natural log, is equal to RT plus C. Or raising both sides to the power of E, we get P over K minus P is equal to CE to the RT, using that trick of pulling out the constant. Okay, just to speed this up, I'm going to go ahead and just for a moment label this as U, and so then that would give me P over K minus P is equal to U, or P equals KU minus PU. Collecting like terms, we get P plus PU is equal to KU, or P times 1 plus U is equal to KU, or this gives us P of T is equal to KU over 1 plus U, which is equal to KCE to the RT divided by 1 plus CE to the RT. This is a fine place to leave it. There's many other things I could do. Let's go ahead and divide both the numerator and the denominator by CE to the RT. Or put another way, I guess we could say let's factor out a CE to the RT from the numerator. That would give us K. And if we divided out a CE to the RT from the denominator, that would give us 1 over CE to the RT plus 1. These then cancel, so we end up with K over 1 plus 1 over CE to the RT. And all I'm doing here, folks, is I'm just doing some algebra to clean up my final answer. So this gives us 1 over 1 plus, so I think you should agree that this would be 1 CE to the minus RT. But then this constant right here, 1 over that constant, is again just an abstract or arbitrary constant, so we get K over 1 plus CE to the minus RT. So that said, we found that P of T is equal to K over 1 plus CE to the minus RT, and this is a version of the logistics growth equation that's completely unlike anything the author mentioned in this textbook. So I'd like to take this version and now use it. Now I'd like to use this in solving the differential equation on the other page. Let's see here. Let's copy that. Oops. Let's try it again. Maybe I'll edit this out because this is taking forever. All right. Copy. I guess that's the paste button. One more time. That must be copy. So let's paste that here. Okay. So now we're ready to tackle the question from the WebAssign. We're told that the number of people who view the advertisement is governed by the logistics equation with n of 0 equal to 200, n of 1 equal to 400. So we know that P of T then would be equal to, so we're given the carrying capacity in this problem, which is why I wanted this version of the solution, CE to the minus RT. So then the fact that n of 0 equals 200, oops, I guess I should be a little more careful here. Let's call this n of t for this problem. N of 0 equals 200 gives us 200 equals 20,000 over 1 plus CE to the minus r times 0, but that's just 200 equals 20,000 over 1 plus c. So multiplying both sides by 1 plus c and dividing both sides by 200 gives us 1 plus c is equal to 20,000 over 200, or 1 plus c is equal to 100, so c is equal to 99. So at this point we know that our model is n of t equals 20,000 all over 1 plus 99 e to the minus rt. And now we'll use the fact that n of 1 is equal to 400. So we get that 400 equals 20,000 divided by 1 plus 99 e to the minus r times 1. So multiplying both sides by 1 plus 99 e to the minus r and dividing both sides by 400 gives us 1 plus 99 e to the minus r is equal to 20,000 divided by 400, or 1 plus 99 e to the minus r is equal to, let's see, it would be 2 zeros would cancel, so we get 50. So we get 99 e to the minus r is equal to 49. E to the minus r is equal to 49 over 99. We take the natural log of both sides, then we would end up with minus r is equal to the natural log of the absolute value of 49 over 99. R is equal to the opposite of that, which if you get a decimal approximation on that, let me see, what did I get? I got approximately negative 0.703299. And if you look now at our model, we have n of t is equal to 20,000 all over 1 plus 99 e to the negative 0.70. Let's go 33 t. So this is our final logistics model explaining the growth of this advertisement. I hope this was helpful.